can never know like because the questions are so nuanced and like the proofs are like maybe yeah.
Yeah, you mean 5 points?
Okay, so how about some infi?
Infinite.
You into it? Yeah. Let's go. Well, a reminder, we know that talked about the improper integrals last week. We know that first of all, the integral of 1 above x to the power of p is convergent or converges, whatever, if and only if p is greater than 1. And secondly, the integral from 1 to 0 can be generalized to the integral of x minus a to the power of some p. The main point is that there is a problem, as we called last week, in the left end of the segment. Convergent, if and only if, what about close the tab. This convergent if and only if is smaller than 1. And thirdly, the comparison test. If f is greater than g, you're writing it in general terms, not getting to specific details. If f is greater than g, then the integral of f is greater than g's, meaning if the integral of f, not if, the integral of f converges, then integral of g converges as well.
Um, or
Yes.
what the second one?
Yeah.
From 0 to 1. Also,
Zero is just an example. The main point is 0 when there is a what you call less weak problem in the left end of the segment. A point that causes the function to be unbounded.
because the x goes to 0, then
Yes, and the function goes to infinity.
uh,
Okay, so similarly to series in the last course, which is very fun. Now, if we talked about convergence, conversion of integrals, and the comparison tests, we can talk about absolute convergence. What happens when I put absolute value on the function as it changes the fact that it converges, yes or no? So let's have a title. Absolute, no, absolute convergence. So you have convergence? That's too much E. Should be A somewhere?
no.
Okay. So the definition is practically the same as we know it. And I want to write it down, see what we can say, what we cannot say about it. It will be similar to what we know about series. So let integral of f be an improper integral. I'm trying to phrase it in a way that both types of integrals, the first type when the segment is going to infinity, and the second type when the function is not bounded, are included in my words of hope. It is understandable. Let it be an improper integral. Hi, how are you? In Hebrew, we say sohavim. Carry on, something like that. If the integral of the absolute value of f converges, we say that the integral of f itself is absolute. Oh, absolutely. Absolute convergent if good reminder to save the file. We are at Tashapu, right? But which Tashapu are we? Should be Infi 2. Two. Sure, 10. Got double digits already. If the integral of the absolute value of f is divergent, but the integral of f is convergent, we can say that the integral of f is conditionally convergent or something like that. No, so it's really absolutely convergent, right? It's an adverb. Is conditionally convergent. Now, important thing to say, probably Aristotle said it as well last year. We have the notion of convergent integral, and now we can add another detail. Does the integral of the absolute value converge as well? If so, then you can say it's not just convergent, it is absolutely convergent. And if not, we can say that it is not just convergent, it is conditionally convergent. Probably it's 1L or 2L here. Now, the interesting examples are the conditionally convergent integrals when we get to it. But first of all, we know that from series, we already know that when an integral is absolutely convergent, it converges. Meaning that if the integral of the absolute value converges, then the integral of f itself must be convergent as well. So I want to write down this as a proposition or a theorem or whatever and prove it. And then after we know this to be true, we can have an example or two for absolutely or not absolutely convergent integrals. So proposition, if, do you want to save it? No. If the integral of f is absolutely convergent, absolutely convergent, then it is convergent. Now let's prove it. It's a nice proof. Don't know how exactly Aris did it, if he did it. In the first course, but when I do it in Infi 1, I'm doing it differently. What I'm going to do here, I'm using the Cauchy criterion for convergence of series. I'm going to do something else, something nicer. Think doesn't involve epsilon.
Can't you use the inequality
Of what?
That the absolute value of something is always
bigger? Oh, it's a good question. It's a good question. First of all, the answer is no, probably, but I want to show you why. It says something important. Why don't you use the comparison test? Meaning, we know that the absolute value of f is greater than f. This is correct for whatever you put in the absolute value. And then, why don't you conclude that the integral of absolute value of f is greater than the integral of f? Meaning, as we know, that if the integral of the absolute value converges, then the integral of the f itself will converge as well. What is the problem with this proof? The problem is with that we don't know that f is always positive, or at least doesn't change its sign when you go along the segment. And the comparison test applies only to non-negative functions or non-positive, as long as they don't change their signs. Now, intuitively, the proposition is very, yeah, because the absolute value of f is greater than f, and if it is converges, then just as you said. But mathematically, there is this one problem. We cannot use the comparison test because we don't know that f is actually positive or non-negative or non-positive. Okay, again, doesn't change its sign. So what do we do? How do we prove it? I want to show you one way. One can think maybe about other ways. Let f be a function. We can define, it's not just for this specific proof. I don't know if you, as computer science students, will see this decomposition of a function more times along your way, but it is useful. It's not the only time we use this nice decomposition. And I want to show you what I'm talking about. We can, of course, we define two functions. Let's denote them with f plus and f minus. By f plus is, let's write it nicely with a bracket from the left side and then conditions on the right side, etc., etc. So 2 rows and 2 columns. Is f the same as f, wherever f is non-negative, and it is 0 when f is negative. About the f equals 0, specifically, one can write it on the bottom line as well. It doesn't change the function. And what is f minus? F minus is always a function that is never negative, but we define it by that way. It is 0 when f is greater than 0, and it is minus f. It is minus f where f is negative. Let's have an example. You always need to see an example in order to start to hope to understand what we're talking about. So, have an example.
How is it different than the absolute value?
The absolute value is the sum of both.
Yeah.
So I want to write, draw an example. 4 functions, f plus, f minus, and the absolute value of f. For example, let's have some nice function that goes up and down in sinus x in from 0 to pi. Classic. So it's too much to draw it on the beige background. I need to use the annotation.
You can use the decimal or your if you want.
Yeah, but we're already here, so
Yeah, why not have fun?
yeah, on the Zoom. Use the Zoom. Oh, I don't need the y-axis. I just need the x-axis. So, 4 functions. It's 4 lines. Should be the same height, parallel. That's what's most importantly, but not very important. Okay, so don't look for the exact proportions or a beautiful drawing. Just what I'm doing here. F looks like a hill and a valley. Yeah, that's sinus x. That's f. Now, we know the absolute value of f. Let's write it down with different color. Let's say green. The absolute value, geometrically speaking, it works like a mirror. Whatever is under the C, what is ever under the x-axis goes up. So that's the absolute value of f. One, as mentioned, can use some mathematical websites or whatever to draw it more precisely. Now, what is f plus? F plus is the same as f wherever, no, not it blue, wherever f is above the x-axis, but then when f is negative, f plus is just 0. taken the line to watch it. That's F plus. And what is F minus? F minus is, let's write it down with, I don't know, orange. F minus is 0 when F is negative, is positive, and then it is not F. It is the minus of F, like the part of the absolute value, when it is negative. So this is F minus. Or now a specific example. Let's now take a picture.
Now there is component that with electricity from one yeah, we'll refer to parts as or diode in a way that you can make up prevented through your charge. It looks like that it goes. That's me.
So now we know that, and moreover, if you want so, the absolute value of F is defined by F when it's positive and minus F when it's negative. And for a complete picture of the situation, it's probably a bit silly, but let's write it down as well. F is F when F is negative and F when it is positive. And now we have four functions. F plus and F minus on one side, and F and the absolute value of F on the other. Now, we have that the absolute value of F is F plus plus F minus. Yet again, maybe we write them down here as well, or for the PDF maybe, for us to have a look at it. Oh, they're both here, all the four of them, and now all four of them. So F, the absolute value of F is the sum of F plus and F minus, and the function F itself is the difference between F plus and F minus. If you sum these, on the first line you get F, on the second line you get minus F, which is absolute value. If you subtract, on the first line you get F, and on the second line you get F minus minus, which is plus F, which is F on the bottom line. And now, we know that the absolute value of F converges. And specifically here in our proposition, we know that what is always true, that first of all, the absolute value of F is greater than F plus and F minus both. And secondly, F plus and F minus are both non-negative functions. And we can see it in our drawings as well. Now, the absolute value of F is greater than F plus and F minus, and they are both non-negative as well. So we can use the comparison test. That's how we get over the problem of F being not necessarily positive, or at least not negative, and we cannot use the comparison test, or very sad. We decompose F to the difference between F plus and F minus, and F plus and F minus are non-negative functions, so we can use the comparison test when we talk about them. So we can use the comparison test. We know that in our proposition, the integral of F convergence or is convergent. So both the integrals of F plus and minus, no, F F minus are convergent. Now, and it's not comparison test, it's just linearity or arithmetics or whatever. If both integrals of f plus f minus are convergent, the difference between them, which is the integral of f, is convergent as well. Finally, integral of f is convergent as a difference between convergent integrals. Integral of f is the integral of f plus minus f minus, which is the integral of f plus minus the integral of f minus. So the integral of absolute value of f is convergent. We have that integral of f itself converges as well. Now, I don't know if you remember. If you do, I don't know if Eris did it that way when it comes to series, when he did it on the first into one, which is very fun. But that's how we do it when it comes to integral. Any questions about the proof? Yeah. When you go back there?
The definition of absolute f and by f minus f.
This one?
This. No, it's above, yes.
This one?
I'm not. I understand what you're trying to do, but I'm not understanding why it makes sense.
So first of all, that's just f. It's a very, not very, but unnecessarily complicated way to write down f.
What's that little minus thing?
Well, this little line?
Yeah.
No, it's fine. It's just the way of the leaks to create a space. I mean, if I don't write it down, no, I understand now.
Maybe you need a color instead.
If I don't write it down, then it's too close to each other.
You can't do a color.
I can do comma, but it's barbaric. Yeah.
Is it?
It is. The right notation is space, just ellipse. It's not very generous when it comes to spaces. Some so clear problem. I don't know if you look at it and write it down, but you watch here. If I double press space, it'll be like, this is not the double space. Please read. Oh, it's too fat in Hebrew. Please read the how to leaks something. It is a problem in spaces, so I changed to comments by your request.
Whenever you click, I should press tab in my. I think I don't know how to click.
What is your?
No, you know, see that? No. It's because it's dynamic here now.
That's not a problem. Probably if I go deep into the Tetsuga or something, then I can change by hand, the millimeters between the first column of the matrix and the second one of the matrix, so I can widen it, but not now. Any other questions? Okay, so now this is um, actually some kind of convergence test. I mean, one can look at the integral, and the comparison test will not work because it's not always positive. And on the other hand, calculating it by definition of the limit, etc., is complicated as well. But when we look at the absolute value of the integral, it is not very hard to tell that it is convergent, and so the integral of f itself converges as well. So let's have an example for that. For example, we look at numbers you like.
Um, you're asking for a number.
Yes.
420.
420, okay.
For the other day.
For the others is the answer for everything. Now, intuitively, this integral is very convergent. For p greater than 1, it is convergent, so of course for 42. But because of the sinus in the numerator, we cannot use any of our comparison tests, and two of them, right? Because the function is not always positive, and not always negative as well. And on the other hand, calculating it by definition, the limit of 1 to b, is complicated as well. We don't know to calculate this integral. I personally, maybe you know, I don't, I'm not familiar with an antiderivative of this function. But when we look at the absolute value of the integral, it becomes very easy. Maybe I'm exaggerated, but it becomes easy, not very. Now, let's write down in short ways. On one hand, comparison test, the comparison test are not relevant here. That's not relevant. The function intersect above x to the power of 42 is not always positive or non-negative. And not always non-positive as well. If it was always negative, we just put minus outside or something, it will be fine. It's just multiplying by a constant, but it changes what?
Nah, I had no idea where you were going with it. Now I understand.
Okay. We're going to the high text, aren't we? Yeah. And not always non-positive. On the other hand, no, before that. On the other hand, calculating it by definition is complicated, or saying the least. We're not familiar with an anti-derivative of sinus x above e to the power of 42. But we want to, of course, using the absolute convergence is pretty easy. Now, with all due respect, the sinus x not greater than 1. And the denominator is always positive, so it's just the numerator causing problems here. Hope the fuss is about it. And now, function is positive, and we can use the comparison test. The integral of 1 above x42 converges. The p here is 42, which is greater than 1. Last time we checked. So our integral of absolute value converges. Well, by our last proposition, we know that the integral itself, the integral of x without of f without the absolute value converges. Because the integral of the absolute value converges. So we can think about this proposition as another convergence test. It's not always working. We know about the concept of conditionally convergent integrals, and we will shortly have examples of them as well. But whenever you have like, okay, it's sinus, it doesn't intuitively actually matters for x 42 or x squared or whatever. What matters is the power of the denominator. But on the other hand, formally, we cannot use the comparison test and we cannot find, or at least easily find, an antiderivative. So this proposition um, comes forth and helps us with this kind of integrals. Okay, so proposition, approved, example, it's all very fine. It sounds like it's in Infi we are like we're going good with it. The tempo, what we are doing or what we're not doing, but some linear algebra, I feel like we are always running after the syllabus. Need to change something maybe. It's more technical. It's more uh, all these long, boring algorithms. I hope it changes. It should change somewhere along the way. And okay, any questions about our example? Nice, good example. We're having the best examples here. Okay. In order to give you somehow simple, not simple, but somehow simple example for a conditionally convergent integral, we need to have some convergence test that know to different, don't say difference in a verb, differentiate, separate. Let's go with separate. Separate between convergent integrals and conditionally convergent integrals. Right now, all of our proposition and test can't do this. Comparison tests work for positive functions. And absolute value of positive function is just the same as the function itself. Now, a proposition talks about cases when the absolute value of the function converges as well. I don't want it. I want when the integral itself converges, but the integral of the absolute value does not. I can show you an example where we can calculate the integral by definition. Maybe near practice / homework. We'll do this. I don't want to waste our precious time on such examples. I want to use our last convergence test in order to show you an example as this, such as that, and our test is the same, or probably phrased the same as the equivalent test from the first quiz when it comes to series. It was Dirichlet test, and the test of Dirichlet, the one, it has a specific case which is called Leibniz test, but in general case it's called Dirichlet. So I want to write it down. Dirichlet, that's how you write his name, I think. Dirichlet test. And as I said in lecture number 6, when we talked about the fundamental theorems of calculus, I use conditions that are probably stronger than I need. I mean, I can prove the test is correct when we use slightly weaker conditions, but the conditions um, I use them in the conditions that I use in the sentence are first of all enough to whatever you want to do, whatever exercise you want to solve here in our course. And secondly, most importantly, when we talk about the lecture, they are making the proof of the test not very long. I'm not saying short, but not very long. So I want to use them as well. But let's first of all write down the test, then have an example, and then we can prove the test, and then we see how much time is left. Dirichlet test. So we have we look at an integral, let's say from a to infinity. No, it's right. From a to infinity of the multiplication of some two functions f and g, where or when, why does f and g satisfy, it's a plural, satisfy, that's right, satisfy the following conditions. It's a bit long list, but it's not very long. First of all, I want f to be a decreasing function. It can be increasing. Let me just put out minus outside. F is decreasing in, of course, segment from a to infinity. For example, 1 above x and stuff like that. Secondly, f goes to 0 when x goes to infinity. One can say that f is decreasing to 0, just concluding both of our first conditions in one sentence. Thirdly, f is continuously differentiable, meaning that it is differentiable and then the derivative is continuous. It's EI or EG when I want to explain something.
Example. You can do IE or EG, I think.
EG, whatever. EG, F tag is continuous. Now, what about G? G, I wanted, first of all, to be continuous as well. Now, here, probably G being integrable and not just continuous is enough. And not continuous, just integral is enough. But yet again, I want to write down that way, make our proof easier, and probably after proof we can talk about why continuous, maybe integral is enough, etc., etc. And the main condition is that the antiderivative of a g, we don't know if it's elementary or not elementary one, the integral of from a to x of gt dt is bounded, not g itself, the integral of g. If all these 5 conditions actually happen, then we can say that the integral of the multiplication of f of g is convergent. Now, I don't know if you remember, if not, will be probably not the best way to do it, but the equivalent test from series, from Infi 1, said something similar. We have a multiplication of two sequences, and we look at the series of an bn, and we need an to be monotonely decreasing to 0, and bn, the series of bn to be bounded, not just bn itself, and then the multiplication gives us a convergence series. So it's something the same. Of course, we need to see an example in order to start to hope to understand what the hell is going on. So, for example, this was the kind of examples probably Erez showed you as well in your first course, which as far as I know was unfathomably fun. What?
The first course
No, wasn't it?
we had fun.
Yeah, extraordinarily. Um, look at a number you like. Any number for the power of x. 24? No. You can write the integral as the integral with L. L. Grand integral is f multiplied by g. Where f is the one above x and g is the trigonometric function. Now, let's make sure that f and g satisfies all the conditions needed. First of all, f is decreasing. It's very simple. I don't want to over-explain it. When x goes to infinity, moreover, f tag, which is x6 to the power of minus 24, so minus 24 goes out, and x6 above x to the power of 25 is continuous. It is not always continuous, of course, but we talk about our segment from 1 to infinity, and there it is good. Secondly, g is continuous. It's just trigonometric function. Moreover, and that's the furthermore, whatever. That's the important part. We want intuitively the integral of g to be a bounded function, and intuitively the integral of sinus is cosinus, which is good, but it's some like own mustache. We need to show it explicitly, not being lazy. The integral of gt from 1 to x. We got gt from 1 to x before gta6, right? It is the integral of sinus t, which is the minus of cosinus t. Yeah, that's the antiderivative. And we plug in t1 and t as x, and we have minus cosinus x, minus minus, it's blues, cosinus 1, which is bounded. Out. Is indeed bounded. So after all, in conclusion, all the conditions f and g, let's write down f and g satisfy the conditions of the Dirichlet test. So the integral of the multiplication is convergent. Any questions? Yeah.
How do you know? How do you know that he's wrong?
Yeah.
How do we know that minus 24 and 25 is like we we have to prove that?
No, I mean, we know that every elementary function that we saw in the first course, we saw in school, is continuous whenever it is defined. So this specific function, minus 24, etc., is continuous everywhere except 0. Now we don't have 0 in our segment, so it is continuous. It's just enough to write down.
So every multiplication of continuous functions is right?
Yeah. And composition, the sum.
Sum of code, right?
Summation, yeah. The sum of two continuous functions is continuous. Okay. So I want to use the Dirichlet, and before we prove it, it's more important to see an example for a conditionally convergent integral. Now, it might be the same as you have simpler examples when it comes to series, or minus 1 to the power of n above n or something. But here we need to use the Dirichlet and work a little bit for it. Now, an example of conditional, it's with double L or just one L? What say you?
I say
Convergent integral. Let's Google it. Double L, you Google it yourself? Okay.
usually we need to like, take away the original was conditional.
Yeah.
The conditional leads go ly. Yeah.
Okay. It sounds right.
Yeah, it's English, so you never know.
It's with every language. You never know until you get there. An example of a conditionally convergent integral. So, first of all, we look at the integral from 1 to infinity of sinus x above x. Here, first of all, on one hand, this integral is convergent by Dirichlet, putting f to be the one above x, and g to be the sinus. On the other hand, let's write down specifically, just like our last example, f is decreasing to 0. The derivative minus 1 above x squared is continuous in the segment from 1 to infinity. G is continuous. It's the same g, so it's continuous, and g's integral is a bounded function. On the other hand, here Dirichlet is our only option. In the last example, could have used absolute convergence. Here, x to the power of 24, we can, as our the previous example, we could just put in absolute value, sinus flies away, and the integral of 1 above x and 24 is, of course, convergent. But when it comes to sinus x above x, first of all, it's a nicer example than the previous one because Dirichlet is their only option. And secondly, that's one our main reason to look at this example from in the first place. I want to show you that this integral is not convergent, it's divergent when we look at it at the integral of the absolute value. Okay, so now we prove that integral of the absolute value is divergent. And it's not so simple. It's not very hard on the other hand, of course, but it's not so simple. And we need to use a shtick or two, including some trigonometric identity. Oh, yes. We missed them. And prove it's too many O's here. What I want you to let's have an agreement about it, that when we add a convergent integral to a divergent one, the sum is divergent. It's true not just about integrals. When you sum a divergent sequence and a convergent sequence, the sum is a divergent sequence. When you sum divergent series and a convergent series, the sum is a divergent series. But I want to explain why and then move on. Before we prove it, we need the following the proposition or something like that. Proposition. If integral of f of some function is divergent and the integral of g is convergent, then the integral of f plus g is divergent. Let's prove it. Different color. Any preferences for the color?
Like white.
Yeah. Not racist at all.
Lime.
Lime, no, it will burn your eyes when you look at the PDF. It's burning as well here on the beige background.
That's a lot.
One can imagine.
Uh,
The lime? Ah, the olive.
yeah.
Yeah. So in Hebrew, "Shatoti im hazayit bayad." You know, the phrase. Olive is good. The intersection between the beige background and the white background of PDF, it works fine on both of them. So approve. You said we assume in contradiction when it comes to Lenech Mashiach?
Yeah. That is true, which applies ABC.
Yeah, he likes all his השתוות. Contradiction that the integral of f plus g is convergent while the integral of f is divergent. Divergent, and the integral of g is convergent. Now, if the integral of f plus g is convergent and the integral of g is convergent, the integral of the difference of them of f plus g minus g is convergent as a difference between convergent integrals. But, alas, the integral of f plus g minus g is what? It's just f, which is divergent by our assumption. Contradiction. So the integral of the sum must be divergent as well. And as I mentioned, generally speaking, if you sum a divergent thing and a convergent thing, the sum is divergent. Now, I want to use this shtick of the sum of blah 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 divergence blah blah, and as I mentioned before, trigonometric identity. How? We need to get rid of the absolute value. It makes the function positive, which is good. We can use comparison tests, but we can't handle it furthermore. We need to look at some function. We can talk about the plus, the minus, etc. So, now, I use, so let's see. The sinus is smaller than 1, or at least is between 1 and -1. When we look at sinus to the power of 2, it is smaller than the absolute value. Both are positive, but when you multiply a number smaller than 1 by itself, it becomes smaller. Yeah, quarter to the power of 2 is 1 above 16, etc., etc. So, and by comparison test, we have the integral of the absolute value of sinus 6 above x is greater than the integral of sinus to the power of 2 above x. Is enough. It is enough to show that the integral of sinus squared above x is divergent. Then, by our comparison test, the greater integral of the absolute value of sinus x will be divergent as well. Now, for my final trick, or our trigonometric. Did I tell you about the TikTok wizard
No,
that I encountered last week?
no.
No? Okay, so last Friday, not last Friday, the Friday before it, someone wrote me on the TikTok chat. Listen, my name, first of all, his username is Nen, Sof, SOF, infinity in Hebrew. And he's got a profile picture of some monster with one eye. And he told me, hey, my name is Eric. I'm living abroad, etc., etc. I'm sorry, I want to learn computer science. So your YouTube channel in Hebrew, taught me in Hebrew. Where should I start? So I thought, good for you, discrete mathematics, Infi 1, linear algebra 1. And then on Motzei Shabbat, he answered me, okay, I subscribed you on YouTube, and as a gift from me, I'll add you 1K followers on TikTok. I told him, okay, thank you. What for? And I was, a bit amused. And he told me, when you have over 1K followers on TikTok, you can add a live link on your bio, and then put the link to your YouTube channel there. I told him, okay, TikTok wizard. And I didn't take it very seriously. I woke up, Sunday, someone along the day, I just opened my TikTok last Sunday, and 1K more followers. Of course, bots, yeah, some ching chong ping pong with the fake profile pictures was 1K followers. Actually, when I going into TikTok now, they're starting to fade away. I mean, I've had let's 1,500. Now I have 1,215, something like that.
The link now.
I've already put it as you requested, the TikTok wizard. But I just had 1K more followers. And I told him, "Whoa, the TikTok wizard! How did you do it?" So you got some, I don't know, a Russian platform where you could do whatever you want, add your followers, views, comments, whatever you like. Yeah. So they did tell me that. Just tell me that's we do it. We talked to him and I asked him, when I entered my the live link he wanted in the bio, he told me that if I reach 10,000 K followers, then I can open some other features from TikTok. Just like the 1K followers open the feature of putting a live link in your bio. So I told him, how can you, do the magic of 10,000 to 10,000K new followers? But he didn't answer. And yes, and my just like the avatar when I most needed him, he's gone. And TikTok wizard is gone, and the bot followers are starting to fade away, as I mentioned. But I'll keep you updated. There are some new new adventures with the TikTok wizard. Now, why did I mention the TikTok wizard? Ah, because I want to show you my last trick. I'm the trigonometric function wizard. When it comes to sinus, yeah, no, that's for the children. Our favorite, for you, about favorite with U after the O, right? Or it's the same for the American English? That's all right, favorite? I don't know. The favorite, trigonometric identity. I don't, but it's useful, this. I don't want to work with squared functions, so I put it out, and I always do it in my head. It's 1 minus cosinus 2x above 2. Gives us yields. I like the word yield sometimes. Let's about yields. Oh, it's vice versa with the E and the I. That the integral is the integral of 1 minus cosinus 2x above 2, and all that above x. And we can write it down is the integral of sum of two functions. One is, let's put the half out. It's 1 above x minus cosinus 2x above x. Now the half outside the integral is a constant. That doesn't changes the convergence. Doesn't change the convergence. The integral of 1 above x is divergent. So by our last proposition, when we proved in the olive color, we only need to show that the integral of the second function, cosinus 2x above x, is convergent. And then the integral of the difference will be divergent, as we want it to be, is convergent. And why is that so? It is true because of Dirichlet. Putting, that's two, double T, not double I. Putting F to be 1 above x and G to be cosinus 2x. F is yet again decreasing to 0, and the derivative minus 1 above x squared is continuous. On the other hand, G is continuous, and the integral of G, which is sinus 2x above 2, is bounded. All the conditions are true, are happening, and by Dirichlet, this integral is convergent. Let's write it down, but don't short. We have f as a decreasing function that tends to 0 when x goes to infinity. With a continuous continuous derivative, which is, I hope everyone outside is all right. And G, a continuous function with bounded antiderivative, derivative gx, the integral from 1 of x of gt dt, the integral from 1 to x of cosinus 2t dt. The antiderivative is sinus 2t above 2, and we have to put x is, no, t is 1 and t is x, which is half of sinus 2 minus sinus 2x, and sinus bounded of this function is bounded as well. So by Dirichlet, this integral of cosinus 2x above x is convergent. The integral of 1 above x is divergent. We showed it last week, and we mentioned it when we started this lecture. So by our proposition, which we proved with olive color, the difference between them is a divergent integral. And so our original integral, which is greater than this integral, is divergent as well because of comparison test. So in conclusion, the integral of sinus x above x is on one hand convergent because of Dirichlet. On the other hand, the integral of its absolute value is divergent because of Dirichlet and other friends. So by definition, it is conditionally convergent. Well, that's a nice example. As I mentioned, it took some time, so we had a little story break about the TikTok wizard. And yet again, one can have an examples of functions that we can calculate the integral using the definition. The limit goes to infinity, but it will be more complicated, and I allow Nir to do such examples. Yeah.
So first we use the research tool that is conditional convergence, and then try to fully calculate the convergence of status, basically.
No, so as I mentioned, we work, it's two steps. First of all, we show that it's convergent without any interpretation about the absolute convergence. And then after we know that this is convergent, we talk about the integral of the absolute value. And then when the integral of the absolute value converges as well, we say that the original one is absolutely convergent. And when the integral of the absolute value fails to converge, it is divergent, just like in our example, then we conclude that the original integral is conditionally convergent.
So we prefer to prove conditional convergence then.
We prove convergence without the absolutely on conditionally, just convergence. That's where we can use definition. That's where we can use Dirichlet. We practically cannot use the tests because the integral will probably will not be positive. But after we prove that the integral is convergent, we can talk about its absolute convergent. If we look at the integral of the absolute value, does it converge, yes or no? Any other questions? Okay. So I want to prove the Dirichlet theorem. And first of all, let's hope we'll finish the proof before we finish our class, our lesson. And then if we do have time, on the other hand, time left, a minute or two, let's see what we can do with this minute or two. So let's get down another line on the proof of Dirichlet test. We know that f is decreasing, f goes to 0, when x goes to infinity, f tag is continuous, g is continuous, and lastly, the integral of g, which we call it big G, can be my ref name, right? Big G and little f is bounded. What we want to know that the integral of f multiplied by g convergence or is converges or is convergent, whatever. You're more of an adjective guy. Is convergent. Okay, these students, you tell me. When we want to handle an integral of a multiplication, what integration method we can try to use? Integration by parts. That is correct. So we use, let's result by definition. What was we actually trying to do? By definition, the integral of f from a to b. One can write it down with all the dx, whatever x explicitly, is the limit some b tends to infinity of the integral from a to b. And as you say, splendid. We use integration by parts because we look at the multiplication inside the integral. Integration by parts. The integration by parts say that we can integral as usual when I try to find the antiderivative. I don't write, of course, I write the limit, but I don't write the boundaries of integral as well. Just write down integral and finding the antiderivative. F of g is the integral of f and big G tag. So we can write it down as f multiplied by big G minus the integral of f tag multiplied by G. So our limit is the limit of the integral. Let's have a big parenthesis over it. Is the limit of the integral of f tag big G. And here we do not have an integral, so we can just plug our and oops. When we plug A and B, we have right direction. F A B big GB minus FA big GA. Before we continue with the integral left with us, I want to explain why both of these nice little fellas tends to 0. Now, first of all, firstly, g of a, as we define g to be the integral of little g of a is the integral of little g, straight g homie, from a to a. And as we define in lecture number 6, what is integral from a to a? Whatever the function is, it is 0, correctly. Say correct. So do the leaf. Yeah. Secondly, what take the leaf from? What about FBGB? It is no 0 doesn't equal 0, but we know that f goes to 0 and big G is bounded. So the limit of a multiplication of a function that goes to 0 and a bounded function is 0 as well. In Hebrew, I call it afisa kaful hasuma. Function that goes to 0 multiplied by a function that is bounded, because f tends to 0 and G is bounded. So both of these expressions goes to 0, and we are left with our integral. We are left with limit of the integral. If you want to be precise, you can say, hey, it's minus of the integral. But on the other hand, we know that we are talking about convergence, and multiplying an integral by -1 does not change the fact that it is convergent or divergent. So I can let the minus go and stay with integral itself. Um, so the limit of the integral is the infinite integral. We need to show that the integral from a to infinity, f tag big G, is convergent. Yeah, but as I said, we're talking about convergence. So the minus doesn't change the fact that the integral converges. It's multiplying by -1. And multiply by a constant doesn't change the fact that the integral is convergent. So it is enough to look at the integral without the minus. Now, how do we do that? Because we are running out of time and moving straight forward, we look at the integral of the absolute value. We show by our proposition, one of the propositions we showed today, proposition is enough to show that the integral of the absolute value converges, is convergent. So we know that big G is bounding. There is some m greater than 0, such that big G of x is smaller than m for every x. In our segment. So the absolute value of f tag x is smaller than the absolute value of f tag multiplied by m, which is m, the absolute value of f tag. By comparison test or the comparison test, we know that the integral of the absolute value of the multiplication of f tag and big G is smaller than the integral of m multiplied by the absolute value of the tag. And yet again, m is a constant. We can put it outside the integral. It doesn't change the fact that the integral is convergent. And it is enough to show that the integral of f tag is convergent. So the smaller integral of f tag multiplied by big G will be convergent as well by, yet again, comparison test. This inequality is what we called in lecture number 5 the monotone, the fact that the integral is monotone. I mean, the integral of a bigger function is bigger. Doesn't originated in the comparison test. It's a more basic notion. Okay, what is integral of f tag? The antiderivative of f tag is f, right? But the absolute value holds us back. If it was just f tag, we would, okay, it's the antiderivative is f, we'll put the limit, etc., etc. But it is the absolute value of f tag.
We are trying to confirm this conversion.
Yeah.
Can we use what we did at the start of the lecture?
Like?
That I know absolute value is bigger always.
Mm-hmm. That is the problem. What is the solution?
If
yeah.
If the f goes to 0, f tag goes to 0, and if f tag goes to 0, the absolute value also goes to 0. That's enough. I know, because
assuming everything you said is true, which is probably not, the fact that the function goes to 0 doesn't necessarily mean that the integral converges. Yeah, which is right. It's true with series as well. We'll talk about it on Tuesday. If the integral convergence, what does it say about f? It always goes to 0 and vice versa. Will be an interesting lecture as far as infinity 2 is interesting. But no, we have a different point to make here. In every mathematical theorem, proposition, whatever corollary, we use each one of our conditions. Which one we didn't use now by now? F goes to 0, we used it. G is bounded, we used it. F tag and G continues, probably on the background, needed to be integrable, etc., etc. But what about F is monotonely decreasing? Now, because F is decreasing, f tag is negative. Yeah? And so the absolute value of f tag is minus f tag. Because the absolute value of something negative is the minus of it. And we get the integral of the absolute value of f tag is, I do two things. One is to write it down by definition as the limit of the integral from a to b. And the second one is to write down minus f tag instead of absolute value. Now let's put the minus outside and on differences side. The integral of f tag is, the antiderivative is f. So we have f in a and b. Now it's the minus of the limit of fb minus fa. All right, you told me before the last nail in the coffin or something like that. fb goes to 0. We are left with, on the bottom line, fa. And the integral does converge. In conclusion, we proved our theorem. The integral of f tag multiplied by big G is convergent by comparison test. It's smaller than something that is convergent. It's actually absolutely convergent, as we shown along the proof. And Dirichlet is true. Now we can discuss, but time is very short, so we are probably not going to do it. Discuss the conditions. Why do we actually need f tag to be continuous? Isn't integrability enough? Isn't Jewish people suffered enough? Why do we need G to be continuous? Is integrability enough as well? But our time is up and our minds are down, so we'll leave it to the next semester or something like that. Yeah, you don't have it. It's a shame. But I don't know what the last like. Okay. Any questions about the proof or anything else we did today? All the fun, the extraordinarily fun we do every day. Yeah. Okay. So, if you write it down, we'll give you another minute to look at it. And then we go each one to his own way. What lesson do you have next? What class? Or the next class? It's with Neo. Okay.
But it's both when you have that.
Yeah. I was talking with an engineer from Amazon about
Engineer from Amazon.
yeah.
Okay.
He came to give a presentation, and I was talking to him about load, and he was telling me I'm always